Yeah, hi guys. Thanks so much for being here. Appreciate you taking time to chat. I have a very, I think, interesting topic today about multi-phase flows and bioreactors and fermenters, a couple of different strategies for simulating these systems. Our talk today is motivated by batch, continuous phase, multi-phase, I should say, bio and chemical engineering processes. So we're talking about sparged bioreactors, fermenters, as it were. We're looking at understanding how bubbles come into the system, what sort of bubble size distributions we get, what sort of mass transfer rates we realize, bubble dispersion, interfacial area, etc. We're looking at kind of these multi-phase, multi-physics processes involving sparge and added gases to these typical batch or continuous flow systems, as it were. So again, key physics of relevance to us, gas flow rates, agitation, breakup, coalescence, those physics, as it were. Looking at, again, collision density, collision frequency relative to the flow field, as well as the nature of the bubbles as they come out of the sparge and predicting its initial bubble size or whatnot. So all these kind of process-relevant physics are what we're interrogating today and developing strategies for attacking as we try to characterize these things in silico. As a quick headline here, we're going to be talking about three general representations. First are fully Eulerian models, where we're resolving both phases explicitly using Navier-Stokes and looking at how the gas bubbles move through the aqueous phases or how they break up or they coalesce. The very first principles framework for looking at, again, transport inside these systems at a very foundational level. We'll also talk about so-called Eulerian Lagrangian particle models. Now, in these particular models, we're adding spherical bubbles with a specified diameter at a specified injection rate to a system and using semi-empirical breakup and coalescence mechanics to predict how the bubble size can evolve through space and time due to breakup with eddies and coalescence events as bubbles collide, as it were. This requires a sprinkling of semi-empiricism, as it were, so it doesn't capture all the physics of the first principles model, but it scales more effectively. And last, we'll talk about partial models. Partial models are by far the most abstract of these three, but nonetheless, they allow us to access very high KLA, large systems, where we can in fact have both bubble sizes and mean-free paths that are very small compared to the integral scale or Taylor scale, and allows us to do more of a sampling of the fluid mechanics as opposed to explicit simulation of the fluid mechanics. I'll speak to all three, but these are kind of the roadmaps where we'll be going. And here, let's start off with these Eulerian models. So these are our most general and first principles means of describing these multi-phase flow physics. Within the context of these systems, we have some sort of gas that's explicitly modeled using Navier-Stokes equations, pushing through some fluid, which is likewise modeled using Navier-Stokes equations, as it were. So we're solving Navier-Stokes equations in both phases, which can have their own densities and viscosities. And we have a surface tension, of course, to find an interaction between those two phases, as it were, as well as a phase field that describes where this interface exists. This is a very high fidelity approach. Again, we're tracking the movement of this individual interface. We're making no comment on the structure of the interface. We're making no comment on what the breakup or coalescence mechanism might be. We're making no comment on what the shape of these bubbles might be. All we're saying, all we're believing is that Navier-Stokes exists. We have these individual fluid properties. There is a surface tension. There is a phase field. Let it go. Now, to do this type of simulation, we have to have a high resolution because as we resolve the shape of this bubble, we have to be able to see the interface. So this anchors, as it were, how much resolution we need to resolve bubbles of a given size. We're going to need, 5, 6, 4, 7-ish lattice points across each bubble, at least, to resolve this extent, as it were. So again, what this looks like in action is typically very useful for smaller systems. This is an Amber 250. This is operating at an impeller speed. I think this is 284, the lower impeller speed. We're not getting much breakup. But again, we're not telling the code to do anything. We're just specifying flow rates and boundary conditions and all of the multi-phase flow, the breakup mechanics, the bubble shape, the bubble evolution that just happens as a consequence of Navier-Stokes, as it were. So again, what did the price we pay? This had a resolution of 180 micrometers. So I can see probably up to about a 0.5 millimeter diameter bubble. Anything smaller than that, I can't see. It's too small, as it were. My time step is on the order of 1 to 10 micrometers, depending on impeller speed. This simulation had about 60 million lattice points for an Amber 250. That's not a very big system. That's a Campbell soup can at about 60 million points. it's practical to run. I mean, I can run, minutes of process simulation, as it were, but, we're limited. We're limited on our bubble to tank diameter aspect ratio. We've done this for systems up to a few liters, and it's very useful understanding the breakup of coalescent mechanics I'll speak to momentarily. So it's really high fidelity. It's very useful. It's very first principles, as it were, but you got to pay the piper in terms of resolution and resolving how these bubbles evolve. But if you pay that price, your reward is generality, as it were, which is really for these types of systems. Okay, and now as we kind of get these physics out, we can start to kind of understand and try to see how they compare against, say, first principles theory. So here I've got 4 different impeller speeds, and we can see the generality of these models as a function of operating conditions. Now, it's the same physics in every model. It's the same two-phase model, same air, same water, same everything, but I'm changing my impeller speed to change the net fluid mechanics. And you can see the code can naturally handle this very stark change in fluid flow, going from kind of bubbling here to a lot of breakup and coalescence and tumbling, as it were. But foundationally, how did I change the code? I changed nothing, because the fundamentality of the representation can handle this heterogeneity in output because it's so, I should say, robust in first principles. We can start to make some elementary predictions, as it were. For example, I can look at, say, the energy dissipation rate in each of these vessels and compare and then predict what first principles would say the mean bubble size should be. For example, if I have an energy dissipation rate across this vessel of 1.4 watts per kilogram, semi-empirical literature tells me the mean bubble size should be about 2.8 millimeters. If I have an EDR of about 5.74 watts per kilogram, which is what I have in this vessel at this impeller speed, semi-empirical theory tells me, this is just driving on a chalkboard, tells me I should get about 1.6 millimeters diameter. What's cool here is that the system can reproduce these predictions in semi-empirical theory. I was trying to get those play, I guess not playing. That's fine. And again, the code doesn't know this should happen. In fact, this is kind of a handshake between first principles theory and bubble size and direct solution to Navier-Stokes equations to recover what the semi-empirical set theory might have predicted, as it were. And again, you might say here, oh, well, down here at this lower EDR, correlation says bigger bubbles. Well, here are coalescence limited, right? Yes, that fluid field could host a larger bubble. We're not able to achieve that bubble size because the bubbles coming in are about 4 millimeters, and they're coming in so few and far between. We don't have any coalescence events that allow the bubbles to realize these larger structures. So yes, while the fluid could host a larger bubble diameter, we're not seeing that side of our system because we don't have enough coalescence to realize bubbles of that size. But nonetheless, you can see how general this approach is and understanding how these solid physics evolve through space and time, and it's practical. Yeah, I'm considering smaller lab scale systems here, but it's routine now to be able to characterize systems with this level of fidelity. We can then validate things like a bubble size distribution, as it were. We can kind of take a close look and make sure the bubbles popping out of the sparge are in line. This is kind of cross checks, but it's like a complex elephant. The more we feel the tusks, the tail, the feet, the back, etc., we can kind of confirm that, yeah, we really got the elephant correctly modeled here, as it were. We're not just pointing on the tusks and feeling the sharp and calling it an elephant. We're kind of feeling around conceptually, qualitatively, semi-empirically, etc., and seeing that things check out. And in fact, we can really go deeper with this and validate it against some pretty foundational semi-empirical theory. For example, on a chalkboard, people have developed frameworks for predicting how bubbles break up. That is, if I have a bubble of this diameter and it's interacting with this sort of energy dissipation rate field, with this viscosity, as it were, and that energy dissipation rate is attacking a bubble of this diameter and this surface tension, then I will get a breakup event that produces these two daughter volume fractions. So foundationally, like folks on chalkboards had developed these first principles relationships for predicting how bubbles will break up as a function of the energy dissipation rate and the properties of the bubble. Think surface tension, think diameter, etc. And you can see, and these kind of developed again from these first principles theories. Let's look at these 1 in 10 watts per kilogram, which is where we typically sit in a lot of bioreactors, as it were. Maybe we get to 100, as it were. But oftentimes we get these M-shaped distributions, which are telling us that when a bubble breaks up, as it were, it typically produces 2 new bubbles, one with about 90% of the original mass, one with about 10% of the original mass. And they've corroborated these models against observed data, of course. But foundationally, this all comes off a chalkboard. Like the chalkboard says, this is what we think the bubble should do. We can validate against the measured data, but this is all semi-empirical, and I'd say first principles theory. The code doesn't know this exists, but the code can validate it. as it were, and say, okay, as I've got bubbles coming in here, and as they're undergoing breakup events, I can look and see, well, what did we get when a bubble broke up and I have successive breakups? How did it break up? And lo and behold, the code reproduces these types of physics. And again, this is kind of a two-way validation. In some sense, the code didn't anticipate this. The code only anticipated Navier-Stokes, but it reproduced the shape that was expected from the chalkboard. And so it's kind of saying, well, the code's probably getting this right. And also, the guys on the chalkboard, they probably got it right too. Now, again, we weren't gunning for their theory, and they had some empirical data to get validated against, but it's neat to see that kind of three-way collaboration between simulation, first principles theory, and experiment in terms of what sort of breakup mechanics we're going to see inside this vessel. And also, this works the other way. We talked about this AICHE last fall. If you've got dripping or varicose breakup or sinuous breakup, it works that way too. If we have the dense phase going into the continuous phase, of course. And likewise, it conveys to multiphysics. If I've got gas bubbles coming in, here I'm coloring by dissolved oxygen. These are oxygen-rich bubbles coming into the system. We can see the wake of oxygen that's being left in their trail as they move through the vessel. Look at them kind of piloting through. When they cross the plane here, you can see them leaving a wake of oxygen. So it's pretty easy to generalize this to multiphysics. So all that good stuff we get with M-Star conveys to these types of models as well. And this is really first principle stuff here. This is really first principle stuff. This idea of a two-fluid Eulerian model with convective mass transfer at the walls of at the interface of the bubble, at transferring oxygen to the dissolved phase is pretty sophisticated, but it's tractable. Like these things run in tractable runtimes on familiar resources, as it were. So what are the gives and the gives? This first principles two-fluid model and modeling approach, no tuning. Right? All it takes are physical properties, viscosities, densities, surface tension, etc. That's very compelling. They can handle a very broad spectrum of physics. You know, jet breakup, bubble breakup as a function of impeller speed, and recover a lot of pretty cool semi-empirical first principles theory. It's very easy to couple this other physics, as it were. And you can see complex things. For example, in this guy here, there's actually jetting that comes out of the sparge. Like, you couldn't catch that with a Lagrangian model. You need the Eulerian model to recover that jet that comes out and then later breaks up to recover this. This is a 3-liter system. So we're getting bigger. We're getting to a coffee can here, as it were. So we're getting real lab scale. And again, we're limited by the aspect ratio. Like if we're on a multi-GPU cluster, we can model bubbles that are maybe like 5 parts in 1,000, maybe like a 5 millimeter diameter bubble in a 1 meter tank. Right? That's about how good we can get. Below that, we're not going to have the resolution to see it. If we're on a DGX, we can get a millimeter bubble instead of 1 meter tank. If we're on a desktop, maybe 1 to 100, as it were. We could do like a 1 millimeter diameter bubble in like a maybe like a 10 centimeter diameter tank. But realistically, that's kind of how we're limited in these different scales here. Very foundational, very general, very multi-purpose, as it were, but limited in scope to, I'd say, lab scale systems. So this begs the question. I was like, oh, look, the code reproduces all these semi-empirical theories. The code reproduces all these breakup mechanics, especially from a chalkboard. Well, can we just use those instead of trying to model the interface explicitly? And the answer is yes. So I sorry I didn't have the slide earlier, but we first spoke about this kind of first paper here that we published a couple years back in AIC's journal. This is with BI. I'm now going to talk about these next 2 papers. One with Pfizer, one with BMS, talking about more of this discrete approach, as it were. And the question is this, you know, we've got this great theory that says, okay, if a bubble goes up and sees a certain EDR, this is how it's going to break up into 2 daughters, as it were. Likewise, you have this great theory that says if 2 bubbles are coming and they hit each other with this collision Reynolds number that's above a certain value, they're going to coalesce. If not, they'll bounce. And we've corroborated this theory against the very foundational two-fluid model. But those simulations are expensive. Like, what if we just treated the bubbles as Lagrangian objects that just broke up and coalesced according to these rules, as it were? Like, okay, we need to assume the bubbles are spheres, so we got to worry about bubbles probably like a few millimeters and smaller. Now, we likewise have to like define an ejection diameter, because whereas the previous simulation, when it was bubbling in, we made no comment on diameter. Navier-Stokes and surface tension just decided the initial diameter. So we need to specify diameter, and we need to evoke some of these semi-empirical theories. But if we can get away from resolving that explicit interface, our simulation would be anchored to some micrometer length scale. It could instead be re-anchored to the fluid mechanics length scale, as it were. So if we can start to use a sprinkle of semi-empiricism inside this LES model, we might be able to access a much larger system. And so what does this look like in action? So here I'll play this a couple of times. Here I have Lagrangian bubbles coming into the system. I see some coalescence events because I can see right when they came in, some are swelling up, which means that some bubbles happen to hit each other and per a semi-empirical coalescence relationship, coalesce, as it were. Not all of them, not every interaction led to coalescence, as it were. But then as they rise, they enter into this, and I'm showing energy dissipation rate, which is driving breakup here. As they rise, they eventually get into this high EDR region, and we see the production of breakup events inside this trailing vortex. Now, why are they breaking up? Because we had some semi-empirical breakup theory in here, going back to the one we validated in the two-phase mechanics here, that's saying if a bubble comes into a region with this EDR, then it shall break up, and then we're sampling at runtime what that volume fraction rent should be by constructing and sampling the distribution function. So again, here we're not modeling the actual bubble being, growing out of the spirale, as it were. We're saying this bubble entered the system, and should it interact with other bubbles, these are the rules governing coalescence. Should it interact with a high EDR region, these are the physics governing breakup, as it were. So what we get here is access to larger systems, as it were. And here's, I think, a 500-liter system, as it were. We've got bubbles coming as Lagrangian objects. Yes, we get this nice heterogeneous bubble size distribution due to the ongoing effects of breakup and coalescence. But importantly, we're not trying to resolve the interface. We're just saying, should bubbles interact in this way, then we can use semi-empirical theory to predict how they will break up and coalesce. And importantly, that semi-empirical theory and it's not a function of scale. So again, when bubbles are going to break up and they're about to enter into a high EDR region, as it were, they're not looking over their shoulder and thinking, wait, how big is this vessel? Or when they're about to collide with each other to determine whether they're going to coalescence or bounce, they're not saying, wait up, before we touch, how big is the vessel? These breakup and coalescence mechanics, they are what I'll call intensive and intrinsic. They're scale independent. So if I get them right at 1 liter, as it were, at like 100 liters, they'll work at 1,000 or 10,000 liters. Because foundationally, these mechanics don't look at the bubbles, the system scale, when considering pairwise or individual bubble breakup mechanics. And that kind of mechanistic Lagrangian attack makes these approaches general across scale, because I'm not retuning breakup and coalescence parameters as a function of scale. I may need to get the properties right, like the surface tension and temperature, but the mechanics I don't change. Let's take a look at this in a bit more detail. So here we have just like a 4-liter system, and I have gas bubbles coming in, and I'm showing the bubble size distribution. I'll play this a couple of times again, and I'm adding these bubbles with an initial diameter of 1 millimeter, anchored to the sparge diameter, as it were. And here I'm seeing these ongoing effects of breakup and coalescence. Look at this here. All the bubbles come with 1 millimeter. As they rise into the trailing vortex, there may be breakup events. Should a bubble enter a region where the EDR demands, where the EDR is greater than the restorative forces of surface tension, and ergo a breakup event will occur. Sure, there's some coalescence before it gets there, as it were, as bubbles might bounce off each other, interact, and merge as they're rising. And upstream, way above the sky, we get a lot of coalescence as well, right? Way up here, the bubbles are bouncing off each other, and there's not enough EDR to break them up, right? Foundation, if it coalesces to a large bubble diameter up here, as we showed earlier when we talked about EDR versus bubble size, there's no impetus to break up here. There's no EDR to break up. So if they swell and rise, as it were. The only impetus to break up is in the trailing vortex. So here we got the velocity field, we got the bubble field, as it were. Let's take a look at this bubble size distribution. It's very interesting. So remember, I'm adding these bubbles to the system with an initial diameter of 1 millimeter. I do have to make a statement here as to what I think the initial bubble size should be. Unlike, again, the two-fluid model, which is just kind of spurting out per Navier-Stokes, here I do have to define what the initial bubble size distribution might be. Here I said they're all coming in with a monodispersed bubble size of 1. In the code, of course, I can put in a size distribution. For simplicity, I'm just making it 1 here. So if I go back to my first time step, like there's been a couple of coalescence events, but this histogram of bubbles, the number of bubbles with a given diameter, it's all at 1 millimeter. Before I enter the breakup region, I can see some of this coalescence events. I've got 1 plus 1 made a slightly larger diameter vessel, or bubble, I should say. 2 plus 1 made one more. Maybe 2 plus 2 made one more, as it were. So I'm seeing these discrete bubble sizes due to discrete coalescence events. You can see if you look at, if you actually start adding these volumes together, you get this discrete set of available diameters you can achieve due to pairwise coalescence of 1 to 1, the new 2 to 1, the new 2 to 2, the new 2 to 3, etc. That's going to need to see those dendrites come up. Now, eventually we start breaking up. And once they start to break up, we start to flesh out this bubble size distribution. Like the only way we're getting these sub-millimeter diameter bubbles, the only way they come inside the system is to break up, as it were. Likewise, the only way to get these big boys as well is due to coalescence. So we're getting something more of a continuum. We're seeing some sort of more generalized bubble size distributions, but it's still dominated by that initial bubble size here. This is not a common in all systems. Systems can look very different, as we'll speak to momentarily, but it's kind of cool to see the gears start to turn on this discrete framework where I have these breakup and coalescence relationships governing when breakup happens, whether two bubble pairs interacting are going to coalesce, and how that's manifest, as it were, inside this kind of evolving size distribution. It's just like the two-fluid system. It's very easy to make this multi-physics. Here is, again, looking at an XCR 2000 sparge with these microsparges down below. Here I'm letting the bubbles, I'm coupling them to the dissolved oxygen phase. So looking at the DO, this is colored by DO in the continuous phase, accumulate across this vessel, and I've got breakup and coalescence here as well. If you squint, you can see some bigger bubbles here at the top, as well as some tiny bubbles here on the side. But this is a multi-physics mass transfer problem. The bubbles are fully coupled with the fluid. This is not hard to do. Likewise, we can look at this from the perspective of the bubbles. Here I've got that same bioreactor. I have oxygen-rich bubbles coming in, I should say. They're not losing a lot of oxygen, but they are, these are air-rich bubbles. They're air bubbles with oxygen in them. Here I can see they're losing a little bit of oxygen as they move through the vessel. So we have lower oxygen concentration at the top, not much, just a percent or so. But they are sucking up CO2. So here I've got some sort of bioprocess, and I can see how the bubble composition is changing in time. So I see breakup, coalescence, I see sparging, I see changing composition of the bubble as oxygen is transmitted and CO2 is scrubbed, as it were. So it's very easy to make these multi-physics, which is nice. But again, importantly, I do have to specify some physics, as it were. So again, gives and gets. I'll go ahead and play this just from last time's seminar, because I think it really illustrates this. The gets, in principle, there's no reparameterization between runs. And I'll stand by that claim, is the breakup of coalescence mechanics, they shouldn't be scale dependent. They shouldn't be. Like the bubbles don't stop and think how big the system is before they participate in a breakup event. When two bubbles are about to coalesce, they're not pausing to say, wait. Is this a 1,200 liter vessel or a 10,000 vessel? They just interact per local mechanics. And because we can appeal to that local mechanic, because we're resolving every bubble explicitly, as it were, those coalescence and breakup laws become simple. We're not using some alphabet soup population balance, as it were. We're tracking every bubble explicitly. These models are very easy to set up, and they're very easy to couple to their physics. This is what I showed last time, where I have the bubbles, transmitting oxygen, informing the production of glucose. The consumption of glucose and the production of the viable cell density. This is just a throwback to last month's seminar for the PID bioreactors, as it were. But again, this was all that Lagrangian representation. Okay, what are we giving up? We are assuming that the bubbles are small compared to the eddies. Like I said again, when I say, oh, well, there's an energy dissipation rate around the bubble, and that energy dissipation rate forms breakup, like that statement implicitly implies that EDR around the bubble is well defined. That statement would not be true if the bubble were as big as the trailing vortex, right? Like that's a conflict in my mind. So I need my bubbles in this representation to be small compared to the flow field, as it were. Again, this wasn't a problem for the two fluid model because, again, the bubbles could be shaped they wanted to. But if I'm going to use this discrete approach, the bubbles need to be small such that my fluid properties are singularly defined. I can practically handle tens of millions of bubbles. Okay, that's not a big deal. I can do that on desktop resources. I can model 10, 20 million bubbles inside a bioreactor explicitly. And again, I'm tracking all those bubbles explicitly, which is compelling. But as I get above that, as I get to like 50 million, 100 million, it gets pretty tough. Okay, like the gears really start to grind and things start to slow down even on GPU clusters. So realistically, if I convert this into a KLA, if I'm like in a production scale vessel, like KLAs of several dozen, I could do that. KLAs and fermenters up to like hundreds, that's going to involve hundreds of millions of bubbles. You know, that's going to be tough. If I'm thinking about a large production scale environment, I've got to come up with something more clever, as it were. I do need to specify initial bubble sizing. Yes, I do need to specify a breakup kernel. I don't reparameterize it through runs, but nonetheless, I do need some sort of information to communicate, you know, how these bubbles on a pairwise space are going to coalesce and how bubbles individually are going to break up when they see some high EDR region. So again, I do make some assumptions here, but the generality is very compelling and it validates quite well. Okay, so let's think about this. It's kind of, we've been kind of moving to this train here. We talked about the two fluid models. We talked about these discrete. Let's talk about this now, this other idea of kind of a parcel. And if we can scale this up one more time to yet even larger KLAs and larger vessels. Here's the logic. Here's the logic. Okay, imagine I have a 1 cubic meter vessel with a 10% holdup. High, but not unreasonable. These are fermentation systems. And let's say that I've got like a 1 millimeter mean bubble size, as it were. In fact, that is not terribly atypical. Here's a system like that. Like, there are so many bubbles here. It is a opaque, cloudy environment, right? Like I'm seeing just this bubble field more than I'm seeing the fluid field. So in this types of systems, I'll have hundreds of millions of bubbles, maybe even billions, as it were. That can go from hard to probably not practical as they get up to very large system volumes and or very large holdup. Okay, so this begs the question: how many bubbles do I really need to track to make a reasonable representation? Yeah, it's cool that we can do 10 million, and certainly that simplifies the modeling. We're just doing every particle explicitly. Do I really need to model 200 million bubbles? Is there any sort of sampling I can appeal to? Do the bubbles reach some sort of local equilibrium? Is there any sort of, can I be more clever about saying, okay, instead of tracking every breakup or coalescence event, can I appeal to local equilibrium mechanics to estimate what the bubble size should be at a certain location, as opposed to tracking and explicitly breaking these bubbles up? And we know this idea of parcels comes up all the time in the EM simulation or other Lagrangian simulations. What would that look like here? And how could I use that to bend a corner in these very high KLA systems, as it were? Let's talk to this. Okay, like here is just a 1 meter diameter vessel. I've got a resolution of about 4 million voxels, as it were. I've got a gas flow rate of about 282 liters per minute, 168 RPM, a diameter of about 40 centimeters for the impeller, so about 1.1 meter diameter tank. Again, about 1,000 liters, I should say. 1 meter diameter vessel, a Reynolds number of about 500,000, just under, as it were. If I just hit this with the discrete method, it works. It's fine. I can do this using the discrete approach. I like the discrete approach. It's very general. I get a predicted KLA about 49, measured right in that ballpark, which is great. My hold is 1.4%. My bubble diameter mean is about 0.7 millimeters. There's a snapshot of the fluid field. This simulation has, again, 3.8 million grid points or voxels, yet like 10 million bubbles. And that just from like an information standpoint, there's an asymmetry there. Like, what additional information am I getting by having 3 bubbles per voxel? Right, the voxel represents the smallest fluid element I can see. Wouldn't 3 million bubbles, each carrying the weight or representing 9 million bubbles, I should say, or each wouldn't 3 million bubbles, each multiplying each describing 3 individual bubbles, have the same net effect as 9 million? Like, what new information am I seeing? Like, think of, like, this comes up all the time. Think about the Nielsen ratings or polling, as it were. Like in the US, as it were, there's like TV ratings, like how many millions of people watch the Super Bowl. They don't sample 1 million people. They ask like 10,000, as it were. And 10,000 people reasonably distributed across the US provides a pretty good idea of how the aggregate behaved. So the same logic applies here. Do I really need all 10 million bubbles or 200 million bubbles in some sort of larger fermentation system to understand what the net effect of the breakup and coalescence is going to be? Probably not. And thinking about this more from a physics standpoint, when I was doing the discrete approach, I said, you know what? Bubbles are going to be small compared to the fluid field. So I can say that the fluid properties are singularly defined. What if we took it one step faster and said that the bubble mean free path, that is how far they were between the collisions, was very small relative to the changes in the fluid flow? Said again, what if we pivoted from a ballistic to a diffusive transport paradigm? Again, what I mean, I'm going to make this point twice. That's really, really important. It's subtle but important. And I'll go back to this movie here. This is diffusive bubble transport. What I mean by that is bubbles are colliding with other bubbles all the time. In fact, they're colliding with other bubbles before they even sample a different part of the tank. This is different from ballistic transport. Ballistic transport is where bubbles move a long distance before they hit another bubble, if they hit a bubble at all. And if we have ballistic transport, then those bubbles are sampling lots of different variations in EDR and flow field before they might see a friend. If we're in a diffusive regime, those bubbles are bumping off each other very quickly. They have a small mean free path between collisions, and those collisions are frequent relative to spatial variations in the flow field. So importantly, this transition from ballistic particle to diffusive parcel lends us an ability to down select and reduce the amount of sampling we're doing explicitly. I'll go, but and now I'm getting a bit heavy here. And again, two fluids are light and airy. Oh, just bubbles come in. It's so simple. Particles, easy to. Yeah, you got to specify breakable coalescence, but you got it. We're modeling particles explicitly. Parcels abstract. So I'm going to get into the theory here, but I understand that this is a little bit, conceptual, or I should say, a little bit rarefied. First question is this: if we're going between this discrete versus a diffuse versus ballistic approach, how far apart are the bubbles? Like, how far apart are these bubbles? That's something we can estimate from kinetic theory. We know there's a mean free path for just a set of particles. We can estimate a mean bubble size, as it were. We can then conjure up how far bubble travels before it sees another bubble, as it were. We can conjure up a mean free path. Cofactor is for decoration, forget it. Pi over the square root of 72, we'll call it 1. What this is telling us, loosely speaking, is that the average distance the bubble travels before it sees another bubble is about equal to the mean bubble diameter divided by the holdup. Said again, the mean free path divided by bubble diameter is about equal to 1 over the holdup. So if I've got a 10% holdup, it means that a bubble is going to travel 10 bubble diameters before it sees another bubble, right? That's what this is telling us. So for a fixed bubble size, if I increase my holdup, that means bubbles collide more frequently. There's a shorter mean free path. They hit each other more frequently. They're more diffuse, as it were. So this LM, this mean free path, tells me how far bubbles travel before they hit each other. Okay, let's compare that to the flow field under its feet. Well, there's lots of ways to characterize the flow field, as it were. Integral scale. We can talk about the Taylor scale, etc. But what this is describing here is how the flow field is changing beneath the bubble's surface. That is, how far does the bubble have to travel before it sees some sort of change in this turbulent structure? Okay. And here's how this comes together. If the change in the turbulent structure is very slow and gradual compared to the mean free path, then we have a diffuse transport problem. I'll say that again in the opposite way. If bubbles are colliding very quickly and frequently relative to their advective timescales, if the bubble collision frequency is fast compared to the eddy turnover time, then the bubbles are diffuse. It's nothing but a bubble party up in here as they're bouncing off each other with a little bit of fluid motion carrying the party along down the street, as it were. So foundationally, the faster those collisions are relative to the advection and changes in the turbulent flow field, the more diffuse our transport equation becomes. So we can define a ratio here. The ratio of the bubble mean free path to this eddy length scale, which I'll define here as the Taylor scale. Decoration, forget about it. Decoration's fine, I love it, but forget about the decoration. Just look at this physics here. What is this telling us? Is that for a given holdup, and a given vessel diameter, if I make my bubbles smaller and smaller and smaller, again, for a given holdup, this ratio is getting smaller. That is, my mean free path is getting smaller and smaller and smaller compared to my eddy scale, as it were. I'm becoming more diffuse, right? Again, as my mean free path gets smaller and my eddy sizes get bigger relative to the mean free path, I'm getting more and more collisions relative to advection, as it were. Conversely, for a given bubble size and a given vessel diameter, if I increase holdup, which means I have more and more bubbles, as it were, lo and behold, that's more of a diffuse transport problem. I have lots of bubbles, as it were, that are colliding with each other, frequently relative to spatial variations in the flow field. So the real hook is this: if we can assume that both the bubbles and their mean free paths are short relative to variations in the flow field, we don't have to model every particle explicitly. We can instead treat these particles as mere sampling parcels, as it were. But again, these conditions must be satisfied. We must have small bubbles that are diffuse relative to the Eulerian field, or the continuous phase field, I should say. I'm not going to go into this. This kind of roadmap is in the paper that was published last year. But this gives some criteria about, as a function of operating conditions, when we can say transport is diffuse versus when transport is ballistic. And if it's ballistic, meaning particles travel a long distance, that is, they travel over lots of hills and valleys of the energy dissipation rate before colliding with each other, we can't use a parcel model, right? This idea of local equilibrium goes out the window. We must use discrete, we must use the Lagrangian approach, as it were. But if we have diffuse transport, where collisions are fast and frequent relative to spatial variations in the flow field, then parcels in play. The parcels in play, and this idea of modeling every particle no longer becomes relevant. And so what do? Well, we still have individual bubbles that are moving through the system, but rather than undergoing some explicit breakup event, we just change the number of particles that are being represented by this so-called parcel. So again, yeah, the bubble gets smaller when it goes into a high EDR region, and larger when it goes into a low EDR region, as prescribed by the semi-empirical theory. But once it's there, we don't generate 10 new bubbles, as we might for the Lagrangian explicit approach. We just say now, this particle is now carrying the weight for 10 other implicitly modeled bubbles, as it were. The number scale, the number of bubbles represented by the sampler goes up as its effective diameter goes down. So we can still model breakup and coalescence. We're assuming here that these bubbles are always snapping to the local equilibrium as defined by the local EDR. We're not modeling breakup and coalescence explicitly. We're modeling breakup and coalescence implicitly through the adaptation of the particle diameter and its associated number scale. And this is valid in as much as we have a system that is diffuse, where bubbles are colliding frequently. And again, what does that look like? Like, here's that same system. Here are bubbles, here are parcels. There are differences. Like, for example, the bubble model can correctly predict that some small bubbles will get kind of trained in these corner regions of the vessel. The parcel can't do that, because the parcel says as soon as a small bubble or a certain bubble enters into a region where the EDR would allow the EDR would permit larger bubbles, the bubbles will immediately swell to that larger diameter. Why? Because we're assuming that collisions are so fast and frequent that the bubbles organically snap to the equilibrium size, regardless of, or rather, as informed by the energy dissipation rate. So what this means is that small bubbles won't necessarily make it into corners, as it were, because there were no small bubbles in those corners to begin with. The parcel model wouldn't allow it. Likewise, where the parcel model gets wrong is like up at the top here. There may be some small bubbles that won the day. They rose up, they got there, they didn't collide. So you have some small bubbles here in low EDR regions. The parcel won't see that. The parcel just says, your equilibrium now, we're losing some of the small bubbles. But the parcel gets right, whether it gets right, is where KLA is dominated inside these systems. So here we've got, like in this system here, very small bubbles, as it were, by breakup. And this is where parcel gets it right. It sometimes struggles in the far field, as it were, but where the rubber hits the road in that trailing vortex, that's where it can nail it, as it were. Get that EDR right, get that bubble size right, get that KLA right, as it were. So there's certain things you miss when you appeal to this diffuse transport mechanism, but in areas where we have the most bubbles and where it's the most painful, that's where parcel turns out to be the most right. And we can validate things. This is both in two papers we published. One, the one with BI, the one with Corteva, as it were, where we looked at this both parcel models for bubbles as well as droplets, as it were, so we can reliably reproduce bubble sizes. But we tend to get the tail wrong a little bit. Said again, the parcel model tends to over-predict the number of big bubbles, because rather than saying, okay, bubbles organically collide as you would in the discrete approach, we're just saying bubbles, guess what? You're big now. Hope you like it, as it were. So it tends to over-predict larger bubbles, but foundationally, you can get KLA right. We've looked at this a lot. I want to keep time for questions, so I'll just kind of move through this quickly. It's in the paper. You can reference this in more detail. This figure probably doesn't make a lot of sense without some of the context to provide, but foundationally, the discrete, the parcel, and measurements, they compare quite well in as much as we are in the diffusive regime. I want questions, so let me kind of conclude here. Let's talk about, come up for air, talk about these three models. We started with the two fluid model. This was great. And if we could, that is all we would do. Okay. I would be a happy man if NVIDIA made like a 500 terabyte memory GPU, and I'd never have to do any of this discrete parcel modeling again. If I could run a 1,000-liter vessel with using the two fluid model, I'd be done. I'd never have to worry myself about semi-empirical models or parcel models. I would love to do that. That's all I would do. It's very useful for developing some empirical models, very general, but really it's limited. It's limited to smaller volumes, and I'll even say to KLA, because like to get to a very high KLA in a small vessel, you've got to have very tiny bubbles. But like if we're going to model very tiny bubbles using the two fluid model, we've got to have a very high resolution. So I'd say like out here, like doable, but tough with two fluid, right? Like that you would really, I would say it's kind of beyond the scope right now. Like the physics are there. In fact, this whole landscape could be two fluid. But practically speaking, if you get to KLAs above, which I'm using as a surrogate for bubble size, bubble diameter, bubble hold, etc. If you get, in the high dozens, that's implying a pretty small bubble. Like you're gonna need some pretty dedicated resource to get above that in terms of KLAs in the hundreds. That's gonna in a 1 liter vessel, a KLA of like 500 implies you've got bubbles that are sub-millimeter, right? Like 0.2 millimeters in diameter, and a lot of them. And the number of bubbles doesn't matter. The flow field can handle that, but the size demands a very small resolution. So realistically, this is tough. You've got to either think of something more general or get a bigger computer. If we go to larger volumes, as it were, and these more modest KLAs, like we can use the Lagrangian Eulerian approach. Like again, we need the bubbles to be small relative to the Taylor scale. And that's typically easily satisfied in these higher volume systems. It's not satisfied in low volumes. You can't necessarily guarantee in an Amber 250 that your Lagrangian approach works, because foundationally your Taylor scale might be on the same size as your bubble scale. When I showed those 250s, those bubbles were big. Like the idea of just blindly replacing those with a point mass, squirrely at best. So it's kind of like you need the two fluid down here, but as you get to bigger vessels where your integral scale is larger and your bubbles are indeed small compared to that flow field, then the Lagrangian works great. It gets tough as you get very, very big or to very large KLAs. Why? Is in like a 1,000 liter vessel, as you get above a KLA of like 100, and I'm thinking regular engineering systems, like bubble size a millimeter or whatnot, you get a lot of bubbles. Like over here would be like several hundred millions to billions of bubbles. You can do it using Eulerian Lagrangian. Heck, you can do it using two fluid if you got infinity computers. But foundationally, like it gets tough to resolve all those particles explicitly. Likewise, a KLA of 100 in like a 10,000 liter vessel, that's a lot of bubbles too. Like this perimeter is all like this right side of the perimeter is kind of all over my memory. Like it's not that the physics break down. It's just like, that's going to be hard to model all those bubbles explicitly. Same logic here. This perimeter is this right side of the two fluid perimeter. Like it can span the whole space. It just gets hard to model a vessel that big using two fluid or the KLA that large. The left side obviously is limited by the assumptions of the model. Like for example, we can't go to smaller volumes with the Eulerian Lagrangian because we have to challenge that assumption that the bubbles are indeed point masses. Likewise, if we get below this, well, this can go down to very small volumes, but in principle, there's a lower limit on these guys too. The fluid has to be a continuum, right? If we get down to like nanoliter size volumes, we might want to use a molecular approach, but that's not relevant here. Let's talk about parcel then. Again, the left side of this box is where we're limited by physics. Parcel isn't valid where we have ballistic transport. This is valid for ballistic, this is valid for whatever. But like we got to have diffuse transport. In order to have diffuse transport, we need to have a big vessel with a lot of bubbles. So we're typically talking KLAs like above 100, and we're typically talking bubble sizes like 10, 100,000, 10,000 liters, as it were. Again, because the left side of this band is limited by physics. We're assuming that transport is diffuse, and we're assuming here that the bubbles, as it were, are very small with respect to the integral scale. The right-hand side, well, you can go big. Foundationally, this is where the parcel thrives. It thrives in systems with lots of bubbles and high KLAs. It thrives because that better satisfies the assumption. It thrives in systems with higher volumes and higher KLAs. Because again, the further and further we get away from being from the further and further the eddy size, the bigger it becomes relative to the particles, the more we satisfy the parcel-based approach. So again, these corners, it's not that you can't do them, they're just tough. That's where the memory requirements become the most burdensome. But if you're in the middle of these guys, the approach is what you want to use. So again, the Eulerian Lagrangian, we need the bubbles to be small compared to the Taylor scale, which is the requirement for this bottom floor here. Eliminates the need for the resolution of the interface, as it were, but we do need kernels, right? Going up here does require breakable coalescence kernels, and we need initial bubble size, which isn't hard to conjure up, but it's a thing. Parcels, they're the most, empirical. Let's concede that. They require the most assumptions. They require both the bubble and its mean free path. It's very small compared to the integral and Taylor scale. Okay. And they're not a way. You don't want to use the parcel to intrude into the discrete approach. If you could, only use discrete, right? It's a way to get away from discrete if the diffuse condition is satisfied. Just be aware of that. Don't say, oh, well, I want my Eulerian Lagrangian to run faster. Therefore, I'm going to go to parcels. Okay, sometimes, but not always. It's more of like my Eulerian Lagrangian approach, I can't fit on my machine anymore. Like this has become an untenable simulation for particle count size. Then you go to particles. Parcels don't buttress particles. Parcels bail particles out when you get too many of them, as it were. As a consequence, simply applied to high KLA systems. So this is kind of the landscape here. Guys, that was where I want to speak to today about these three different frameworks here. The gives, the gets, the each. The models I'm happy to share. All of these things. These I can share. Shareable, shareable, of course. Shareable, not shareable. That one on the left, I can't show the geometry. Not shareable. Shareable, as it were. These two-foot models, shareable. All of that is shareable. If you need these, just say the word I can send them out to. Shareable, of course. Shareable, not shareable. But foundationally, it's here. If you want it, you can run these yourselves. Happy to take any questions. Thanks for sticking through. I know this was heady. We covered a lot of topics, but I think we got through it. So yeah, with that, questions, comments, I'm happy to jump to code, happy to jump to the presentations. Let's hear what you got, guys.
Okay, we've got a few questions here. We'll start with this one. So using this Eulerian approach, can we capture what sizes of bubbles are formed from the spargers in a submodel to understand the performance of sparger products without any predefined inlet bubble size, just like BOF?
That's exactly right. That's exactly what this was showing. So like, I'd invite you to turn this upside down and pretend this was air. Okay, at the end of the day, who asked this question? Was this Abhinav?
Yes.
I thought a second. Yeah, okay, hi, Abhinav. So at the end of the day, yeah, like that's the point. So I was kind of like, oh, look, we could do jets as well because the VOF model is that general. But like, in your mind, you could turn this upside down and pretend this is the low density phase, as it were, and look at how those jetting effects, what sort of bubble size we're getting out of the sparge. And in fact, you could use this, Abhinav, to understand what sort of initial bubble size distribution you should feed into a coarser grained model, right? So yes, it'd be tough to do in one. Like I can do an Amber 250. That's what this is. Like note here, all the bubbles kind of come out with about the same size, as it were. So I know what the bubble size should be. It just happened to be this convolution of topology, flow rate, etc. That's the bubble size we get, and it does compare well against what people are taking, what they go to take photos, as it were. But yeah, This model requires no a priori comment on bubble size, as it were. It can calculate it automatically and be used as a model that does require those types of systems. Great question.
Okay, next question. Can you speak to the possibility and practical considerations of simultaneously running the Eulerian-Lagrangian model and the Eulerian-Eulerian model and having some type of transition bubble size to transform a bubble from one description to another? Would this help capture bubbles that are larger than the maximum allowed Eulerian-Lagrangian bubble size?
Yes, this is one of our most active areas of research now. I don't have that in the slides here. It looks like Frank, that's coming from you. But if Johanna's here as well, we can tag team and talk about this. But we're getting better. We call this Lagrangian Eulerian conversion, where we have a continuous phase transition into a discrete phase. Should it go below some critical diameter, the diameter which the lattice can host, as it were? We're pretty good at having continuous become discrete. We can do discrete becoming continuous, but that's trickier. It's trickier as it is for us right now. But I'd say continuous discrete, we do reasonably well. I don't have that slide handy here, and I usually get into trouble when I try to find slides real fast. So I don't want to get myself in trouble. But we do have a little bit of this that we've spoken about before. I just wanted to see if I've got it here. If I can't find it, 2 seconds to move away. I might have it here. I'll load this up. Let me load it up, and it's going to take a minute to download, but I'll show you an example of this. But yeah, it's doable. It's in play. It's tricky, but it's kind of one of our kind of pretty active areas of research. And I'll show a movie that momentarily once we get this guy to come on through. It's just downloading. It's got a few more megabytes.
Okay, should we go to the next question?
Ask the next question. I'll show it real fast.
Okay, in your experience, how inaccurate would you consider a model that employs the parcel method for systems ranging from 1 to 10 liters with a KLA value below 10?
I would quantify that. Like at the end of the day, that would be so easy to simulate using either a Eulerian, a Lagrangian, or maybe a discrete approach. I would try to I don't know, but it'd be pretty easy to figure out pretty fast, by running simulations there. Frank, real quick, here is this in action. Here I have a pipe sparge, and it is a continuous phase. It's hitting the impeller, and then it's shedding satellite particles as it gets dispersed. Okay, this is Eulerian Lagrangian conversion. Okay, and here's a higher VVM case. I'll kind of show this guy here. There's kind of my gas. My continuous phase is then being ripped up into droplets. Frank, this is like pro level. Does that make sense? We're having this conversion, as it were. But yeah, this is where we're going. This is exactly where we're going. And let me not show the Lagrangian bubbles, just the Eulerian interface. But that's the Eulerian interface. And I'm not showing the bubbles that are being formed, but yeah, that's a very, very attractive area of research for us. It's tough, but this is exactly where we're going, Frank. Great question. And I didn't mean to dismiss the question about how bad is it in these lower KLAs. Let me just go back to this slide here real fast. So I think the question was speaking about these points down here, over here. Okay, I might try to use Eulerian Lagrangian, because if Eulerian Lagrangian might be a better approach, because if I've got it's just tough. It's just tough. I understand the question. I just don't want to answer it. I wouldn't do it, because I don't think the parcel approach is valid. But we'd have to come up with some way of nudging 2-fluid over and comparing it to parcel, as it were, to see when parcel kind of broke down in this corner down here. So I don't have a great answer for that, but I understand the question. But it's just I don't want to make a comment on how accurate it is without a lot of homework done first. I don't know who asked that question, but I know I kind of danced around it. Apologies for that.
Okay, next question. Do we actually model the holes on the sparger?
Well, it depends. For the 2-fluid model, you bet. For the Eulerian approach, no. We just say this is where bubbles come in the system. So we can, for example, here I just put 10 bubble sources, as it were, where the bubbles are being added to the system. Likewise with this guy here, I just had a ring sparge. So I didn't model the whole system. I just said, in that region, add bubbles at this rate, the volumetric flow rate, with this diameter, they come in. But when I do the 2-fluid, then I do model that hole explicitly, as it were. Great question.
Okay, next question. If a parcel evolution delay were to be put into the simulation, potentially tied to the local concentration of parcels, could that help to reproduce the corner bubbles and reduce the overpopulation of large bubbles at the top of the simulation?
Great question. The answer is yes. One, in principle, like I have like this zero order relaxation time where it's like as soon as a bubble sees certain EDR, it just like collapses down to this new size. Like in reality, I should have some sort of like relaxation time, Dave. That I just don't know how to tune it or how to set it. So I'm doing a real dumb zeroth order relaxation. But yeah, in principle, you could allow some sort of relaxation operator to inform like the time it takes bubbles to relax. Haven't been that sophisticated yet. And I get a little worried about opening up yet another tuning parameter. I love the simplicity of the instantaneous convergence, but yeah, it's in play. It's certainly in play, and that's how we would do it. That's right, Dave.
Okay, next question. Could I apply your methods to solid particles that can either break up or coalesce?
Sure, but solid particles break up in very different ways. Like there is good theory for predicting how bubbles break up. Solid particle, whether it be dissolution, which is well understood, or other sorts of breakup events, typically we're modeling processes here wherein the fluid EDR causes a bubble to break up. Particle breakup is typically more of a mechanical process, wherein a particle like hits a wall or hits a bell or hits a mill as where it's breaking up. Now we can do that, but it'd be kind of a different family of breakup models than we're showing here, which is a fluid mechanical based breakup process.
Okay, a few more questions. Can you please explain in more detail how is the process of modeling mass transfer in M-Star? Especially interested in understanding the modeling of mass transfer when using an Eulerian-Lagrangian model.
Yeah, right on. So we talk about this a lot in our papers, as it were. Let me go ahead and blast some of these guys away just to clean this up. I was just some slides yesterday. But foundationally, I model this on the level of the individual bubble pairs. So if I want to model mass transfer, as it were, I would go here and interfacial mass transfer. Maybe I've got convection, as it were. I need a KL expression for linking KL to local energy dissipation and fluid properties. Once I have this, I can calculate KLA, right? Likewise, if I have a couple of scalar field here, let me go ahead and add some sort of DO. I know we're at time, so people got to jump. There's no love lost. If I go over here to DO, as it were, let's say dissolved oxygen, I can go to my gas bubbles. This is all in the papers, all in the online documentation as well. I can go here and kind of coupling. I'll couple to my scalar DO here and specify the volume fraction of oxygen, the molar volume and solubility. That's how we do the coupling. Like coupling is very straightforward. Use the Lagrangian approach, and importantly, it's modeled at the level of the individual bubble basis. We're at time. I do want to respect that. Guys, thank you. I'm sorry, Amber, I should hand it back to you. I should probably close. I do want to respect the time, but.
That's okay. We have your questions in the chat, so we can address them, and we'll make sure to get all your questions answered. And as I mentioned before, this webinar is being recorded and will be accessible to you. Thanks so much, everyone, for coming.
Yeah, thank you, guys. Appreciate your time. Bye-bye.